Hi everyone! Welcome to part 1 of chapter 16. Today we are starting our chapter on acids and bases. Acids and bases is a foundational chapter in Chem 2 because it allows us to talk about things like buffers and titrations and all kinds of other cool reactions. So today we are going to start off kind of with some definitions of what acids and bases are. So there's not a lot of math today, but don't worry, there is a lot of math coming your way in this chapter. Make sure you have a good handle on chapter 15 with all of those equilibrium calculations because we are going to use them a lot in the coming chapters, especially in this chapter 16 as we start to apply it to acids and bases. So starting off, why do we need to learn about acids and bases? Well, one really common instance is, you have stomach acid, right? So in your stomach, you have hydrochloric acid, and so that would be HCl. And that HCl is used to kill any unwanted bacteria. It helps to break down your food. It can also activate some of the enzymes that break down your food. We've talked about enzymes before. But sometimes you have too much acid in your stomach. And if you have too much acid, it can back up into your esophagus, right? And that can give you heartburn. It can give you acid reflux. It's really, really uncomfortable. Okay, so if you have too much acid happening, what do? Naturally, you add a base, right? And so these are for mild cases of heartburn. There are other things you would do for more severe instances, but say you just had some occasional heartburn. One thing you can keep swallowing your saliva, which contains the bicarbonate ion. So that would be HCO3 minus, and that will act as a base and neutralize some of the acid. You can also take antacids, right, that contain hydroxide ions or carbonate ions. So one of these would be magnesium hydroxide, which is milk of magnesia. Just be careful, that is also a laxative, so, fair warning. But the point here is that, if you have too much stomach acid, you would, take a base, right, which would neutralize the stomach acid. We don't call them bases, right? We call them antacids. That would be for, the general population. You have too much acid in your stomach, so you take an anti-acid, right? Which is where we get antacids from. So there you go. So let's talk about acids in general. If you've ever had, heartburn or anything like that, you would notice acids taste sour. You would also notice this with things like citric acid. So if you have sucked on a lemon before, right, those are really, really sour. And that's because of the citric acid. Acids are used to dissolve a lot of metals. This is really helpful in chemistry if we need to have a free metal floating around in solution. Maybe we need some iron or copper or something like that. We can put, a strong acid in there and it will dissolve it and it will ionize it, which is cool. It can neutralize bases, which we were just talking about, and it will change blue litmus paper to red. You may not have used litmus paper before. Litmus paper is really cool. So we have a couple different kinds of litmus paper. Blue litmus paper will turn red if you stick it in a base, like I've said here. If you put blue litmus paper in water, right, something neutral, it just kind of looks wet. Same thing if you put it in a base, but if you put it in an acid, it'll turn red. So that's kind of helpful because you can tell whether something's acidic or not, but it doesn't tell you how acidic it is. What's really useful, though, is if you have this kind of orangey, yellowy, tan paper, and that will turn red in acidic solutions. It will turn blue in basic solutions, and it can give you a better kind of estimate of the pH. Anyways, this is acetic acid. This is vinegar. Concentrated acetic acid we call glacial acetic acid. But really dilute solutions we call vinegar. And so you may have had this before, especially if you maybe buffalo chicken wings or buffalo chicken pizza, right? That has that vinegar in it, or maybe you like vinegar on your salad. But you would notice that it tastes sour. So here are some other acids. So up there, like I said, we have hydrochloric acid. We use sulfuric and nitric sometimes in class. Acetic acid, like I said, is vinegar. Citric acid, you see it in citrus fruits like lemons, limes. Sometimes you'll see it in foods or in beverages. Carbonic acid you see a lot, like in your sodas. That's how we make the bubbles, right? Carbonic acid, we know, breaks down to carbon dioxide and water. So that's cool because if you put carbonic acid in your soda, eventually it will become carbonated, which is really neat. Hydrofluoric acid, phosphoric acid, right? We have lots of different acids. But the way that we recognize these acids is we will typically write them with one or more of the H's in the front, which will signal to you that this is in fact an acid. rather than being something like a hydrocarbon. All right, so we have a couple different kinds of acids. The first kind of acid is a binary acid, and this is when we have the the acidic hydrogen is attached to some kind of a nonmetal. So here, like hydrogen is attached to chlorine or hydrogen's attached to fluorine, right? And so we call them binary acids because it's hydrogen and one other element. You can also have things like hydrosulfuric acid, not to be confused with sulfuric acid. This is hydrosulfuric acid. But again, people kind of forget this one's a binary acid because they see that there's 3 atoms bonded together. Well, that's true, but the way that we define binary acids is it's always going to be hydrogen and one other non-metal. Okay, so this is hydrogen, even though there's more than one hydrogen, it's still just hydrogen and one other non-metal. So this is a binary acid. When we name binary acids, we always name it with the hydro in the front. So it will tell you what the nonmetal is. So this hydrochloric acid, it's always going to be hydro to tell you that it's a binary acid. Chlor is going to tell you which nonmetal is on there. And then it's always going to end in ic acid. So this would be hydrofluoric acid. This one's hydrosulfuric acid. You could write another one, right? We could have hydroiodic acid, but it's always going to be hydro something ic acid. That's how we name binary acids. Oxyacids are when we have a hydrogen that's going to be attached to an oxygen, and then that oxygen is attached to a different nonmetal. Okay, so it's always going to be like hydrogen is attached to an oxygen. That's why we call them oxyacids, because we have this oxygen here that's happening. And then that oxygen is going to be attached to another nonmetal. And then usually there's a bunch more oxygens happening. Okay, so like this one, same thing. We have a hydrogen, and then that hydrogen's bonded to an oxygen. That oxygen's bonded to some other nonmetal, and then we have other oxygens happening. That's typically what it looks like. So this one, we have sulfuric acid, we have nitric acid. These ones are from the list of polyatomics that you guys should have memorized, right? We have like nitrate, which was NO3 minus. So if we add a hydrogen to balance out that negative charge, then we have HNO3, and it becomes nitric acid. So this was nitrate, becomes nitric acid. And the way I remember that is I ate something icky, right? You ate something icky. That's how you get that it goes from nitrate to nitric acid. Whereas if you have something like nitrite, right, which has one less oxygen than nitrate, if you put a hydrogen on that to balance it out, make it an acid, then this becomes nitrous acid. And hopefully you guys remember how much fun this is from Chem 1. So if you haven't got the idea yet, you might want to brush up on naming your acids. It will help you out, okay? So we have, these are all oxyacids, okay? Again, always going to have hydrogen attached to an oxygen, and then that oxygen will be attached to a different nonmetal, which has some other oxygens happening. All right, and then our last type of acid that we're going to talk about is carboxylic acids, and this will become really useful in organic chemistry. We do a lot of chemistry with carboxylic acids. And the carboxylic acid group, like I won't expect you to be able to recognize it from this structure, okay? I would expect you to recognize, okay, this is an oxyacid, especially because they come from polyatomics that you recognize, right? These are oxyacids, and I would expect you to be able to recognize a binary acid. So if it doesn't fall into one of those categories, pretty good idea that it's a carboxylic acid, but I'm not going to ask you to identify that it is a carboxylic acid, okay? And the way that they, all of these have in common is this group. Okay, that's a carboxylic acid group. So it's always going to have a hydrogen attached to an oxygen, which is attached to a carbon, and then it's got other things happening. But there's always also going to be this carbon double bonded to an oxygen. So that whole thing is our carboxylic acid group. And then there's like the rest of the molecule over here. But this is the part that's important, this stuff on this side. Okay, when we write these carboxylic acids, only the hydrogen in the first, the very first hydrogen is acidic. Okay, all of the other hydrogens, if we were to draw these out, and I think you can kind of see it here, the black ones are carbons, and then we have the oxygens, and then we have the hydrogens. Okay, but when we have when we have a hydrogen that's attached to a carbon, that's never going to be an acidic hydrogen because the electronegativity difference between the carbon and the hydrogen isn't great enough. Those form very nonpolar bonds. And so the hydrogen and the carbon share their electrons really happily, and that hydrogen never falls off. Okay, what happens here in this carboxylic acid and in the oxyacids is that the electrons get pulled away from the hydrogen, and they just keep pulling them and pulling them and pulling them away until eventually this hydrogen kind of falls off is essentially what happens. And that's what we mean by an acidic hydrogen. Okay, so we need to have the electrons move away from the hydrogen in order for it to be acidic. Okay, so the reason that only one of these hydrogens in this carboxylic acid group is acidic, right, is because it's only this one. Only that one that has this whole carboxylic acid thing going. If we have say there's, a carbon here and we've got some hydrogens and some hydrogens, right? They're not part of this group, and these are very non-polar bonds, so they are not acidic, okay? Again, this will be important somewhat in this class, but especially as you move on in chemistry. All right, let's talk a little bit about bases. So bases, if you were to eat a base, don't taste anything in lab, just putting that out there, but if you were to eat a base, it would taste bitter. One that you may have, tasted, like if you were, maybe you said some bad words as a kid and your mom washed your mouth out with soap. Soap is a very weak base, some types of soap, and it tastes really bitter, right? You made a weird face. So that's where you may have seen it. Again, don't taste the bases. They are often poisonous. If you were to kind of feel a base, and you can do this actually, in one of the labs, not in this class, but in other classes, you can feel a base, a very dilute solution of sodium hydroxide, and it will feel slippery between your fingers. But you can also do this again with soap. If you put some soap on your fingers, it feels slippery, right? It will turn red litmus paper blue. We talked about the whole litmus paper thing already. So if you have red litmus paper and you put it in a base, it turns blue. If you put red litmus paper in water, it just gets wet. And if you put red litmus paper in acid, it just kind of looks wet too. But it will turn blue if it's a base. And then again, it has the ability to neutralize acids. So here's some common ones. We use them a lot in manufacturing, and we use them a lot in chemistry. You don't see them quite so much out in the world, but like sodium bicarbonate, we have that in lab. That, again, we have those in those bottles, right? And if you have an acid spill, the first thing you're going to do is dump some sodium bicarbonate on it to neutralize your acid. And you'll dump sodium bicarbonate on it until it stops bubbling, right? Because the bubbling is the carbon dioxide that's being released because of that acid-base reaction. So as soon as you don't see any more bubbling, you know that it has been neutralized, okay? But you've probably worked with sodium hydroxide before. We use that really commonly in lab. And then we use ammonia quite a bit in this class because it's a really good weak base. Sodium hydroxide is a strong base, ammonia is a weak base, and we'll use those both really commonly. Okay, so we have some definitions of acids and bases. So we're going to cover 3 definitions in this class. We're going to cover 2 now and 1 kind of right at the end of this chapter. The first one is the Arrhenius definition, and that definition is that acids will produce H plus in an aqueous solution. Okay, and you'll see in this class, sometimes you'll see I write it as H plus, and sometimes I write it as H3O plus, and these are the same. Okay, or they mean the same thing. When this H plus is put in water, it will always add on to, it essentially does this, it adds on to a water molecule and it makes H3O plus. Okay, so oftentimes this hydrogen is really floating around this way. This is more of a shorthand. This is more what's like actually happening. Both are correct. Okay, so whether you choose to write it as H plus or H3O plus, just know that they mean the same thing. So don't get caught up on, oh, I wrote it as H plus here and H3O plus there. Same thing. And then our definition for our bases is that they produce hydroxide in an aqueous solution. Okay, so this would be like, we were talking about sodium hydroxide before. And, in solution, it will break into Na plus and OH minus. And for an acid, we could use, like hydrochloric acid would break into H plus and Cl minus. Okay, so that's where we're getting those definitions. And these ones you should have been able to recognize from Chem 1, right? If we have an H in the front, that's going to be an acid. OH is in the back, that means it's going to be a base, right? And so those are really good definitions. But an even better definition is that acids, sorry, and I should have written that these were acids. Acids are hydrogen donors and bases are hydrogen acceptors. Okay, and so we'll look at how that works out, right? Because these examples are only for strong acids and strong bases, and they don't work as well as an example when we start getting into weak acids and weak bases. So this is going to be a better definition than the Arrhenius definition. And so that's pretty much the one that we'll work with. So a little bit about Arrhenius. So here's our example for hydrochloric acid. They produce H+ ions in an aqueous solution. So if you stick this hydrochloric acid in some water, right, it's going to dissociate and it's going to break into H+ and Cl-, and it's going to float around this way. We're going to get into this a lot in this class, but you'll notice that this is a single-headed arrow, okay? This does not form an equilibrium. That is because hydrochloric acid is a strong acid. There are 7 strong acids, and you're going to be expected to know them. You may know them already from Chem 1, but if you don't, they will be covered in this class, but I'm just telling you now, you will need to know which ones are strong acids. So hydrochloric acid is a strong acid, which means it completely dissociates into hydrogen and chlorine. That's why it is getting this single-headed arrow. It doesn't form an equilibrium. It's not going to make more hydrochloric acid. It's just breaking apart. Okay, and so this is a little bit about that hydronium ion that I was talking about earlier. The H+ ions, right? And just so you know, so another word before I get into this, another way of talking about this H+, rather than saying H+ all the time, we call this a proton. Okay, and that may strike you as odd because you have taken other chemistry classes and you're like, well, protons are those things in the nucleus. They are positively charged. They tell you, the atomic number of the atom, but we definitely don't write them as H+. Okay, well, I'm going to digress really quick. So if we think about hydrogen, hydrogen has 1 proton in its nucleus because it's atomic number 1, and then it has 1 electron, in the 1s, to balance out that 1 proton. Okay, so we have 1 proton, one electron. And if we look at the mass number of hydrogen, that mass number is 1. So it's telling you that it has, that 1 proton and it doesn't have any neutrons. So this is a neutral atom of hydrogen. 1 proton, 1 electron. So this H+ here, right? The way that we became H+ is we lost an electron. Okay, well, let's lose an electron. So we're gonna lose an electron. And when we lose an electron, there we are. That's H+. Okay, so it really is just a proton floating around. So when you see the word proton written or H+, those actually mean the same thing, which is really weird. I remember being really weirded out by that the first time I heard that, but it's true. H+ is just protons floating around, okay? Anyway, back to this though, the hydronium ion. So these H+ ions, right, these protons that are being produced by the acid are so reactive that they can't exist in water. They can't just float around by themselves in the water. Okay, instead what they do is they react with a water molecule and they make the hydronium ion. Okay, and so that's what this is. So if you look, all we did, we added on another hydrogen over here. It just bonded with the lone pair from the oxygen. Right, because look at, so this has 2 electrons, right? And we wouldn't normally think that forms a bond, but this hydrogen has no electrons. So that hydrogen can go and it can share both of those electrons with the oxygen, and now it forms a bond, and we can have this hydronium ion H3O+. Okay. All right, so bases. Bases produce hydroxide ions in an aqueous solution. So here we have sodium hydroxide, and again, this is a strong base. Okay, and so since it is a strong base, it completely dissociates in water, so that's why we are having this single-headed arrow. Okay, and so it's completely going to dissociate into sodium and hydroxide. Sorry, we dropped the minus there. And so that's how they are floating around. Okay, but again, this is for a strong base, this whole complete dissociation. So if we were to look at this, right, these, 2 definitions, right, our acids and our bases, our proton, our H+ from the acid will combine with the OH- from the base to make a molecule of water. Okay, that should make sense, right? Here's 1 hydrogen, 2 hydrogens, right? So there's the H2, and then we have an oxygen, we have water. And then the other stuff, right? So the cation that was from the base, maybe that was like, like sodium. And then the anion from the acid may be chlorine, right? Say in this example, we were reacting, hydrochloric acid with sodium hydroxide. They will make a salt. And I want us to be very clear here. This term, salt, in chemistry means ionic compound. It does not mean salt. In this reaction, yes, okay, we made salt. We made table salt. But we won't always make table salt. This means ionic compound. Acid plus base will always give you an ionic compound and water. We call it a salt. And then you'll have to figure out, okay, well, is that aqueous or is it, is it forming a precipitate? What's happening? Okay, but the cation from the base will combine with the anion from the acid to make a salt, and the H plus from the acid, the OH minus from the base, make a molecule of water. All right, so like I said, our Arrhenius definition isn't great for like these weak acids and bases, so we will mostly use this Bronsted-Lowry acid-base theory just because it's more useful and it's more widely accepted and more widely applicable just in general. So anytime we are transferring a proton, okay, so we're going to transfer a hydrogen. In this case, we transferred a hydrogen, right? We gave this hydrogen to the hydroxide is what happened here, right? So we were transferring a hydrogen. So any reaction in which we're going to transfer our hydrogen from one molecule to another, then we're going to consider that an acid-base reaction, even if it doesn't occur in an aqueous solution, even if there's no hydroxide present, even if, right, we're just looking at what is the hydrogen doing. The hydrogen is going to go from one thing to another. That would be an acid-base reaction. And this is important. Anything that fit the Arrhenius definition also fits this Bronsted-Lowry definition. That's how it works out. It doesn't go the other way, right? Not all Arrhenius acid-base reactions would be considered a Bronsted-Lowry acid-base reaction, but all Bronsted-Lowry acid-base reactions, but all Arrhenius acid-base reactions are also Bronsted-Lowry-based reactions. That probably ended up more confusing than I meant it, but hopefully it all works out. This is what you're looking for. All right, so let's go ahead and look at this. The acid is always going to be a hydrogen donor, and the base is a hydrogen acceptor, okay? And the way that the base is going to accept the hydrogen, remember when we talked about this H plus bonded onto our water, okay? And so the way that that happened is because this oxygen had this lone pair. Okay, so that's really important. A base structure must contain an atom with unshared pairs of electrons. Okay, that is how it's going to accept that hydrogen here. Okay, so in this example, water was acting as a base because it accepted that hydrogen. Okay, so in a Bronsted-Lowry acid-base reaction, the acid right here will always donate that hydrogen to the base. And again, that base has to have a lone pair of electrons so it can accept it. When the base accepts the hydrogen, right, when it does that, it's going to gain a positive charge. And then when the acid loses the hydrogen, it is going to have a negative charge. Okay, so keep track of your charges. Okay, again, acids, hydrogen donors. So anything that can have a hydrogen could potentially be a Bronsted-Lowry acid. But we have to look at the structure. That's kind of how I was talking about earlier with those carboxylic acids, where that carbon and the hydrogen, right, we're having a non-polar bond. That is not going to be an acidic hydrogen because of the structure. Usually, like I said, the way it works out is that one hydrogen is going to be easier to pull off the molecule than any of the others, right? It's the easiest to transfer, and that would be what we call the most acidic hydrogen. That's the one that's going to undergo the reaction, okay? And it all has to do with structure. So when hydrochloric acid dissolves in water, that hydrogen, right, that hydrogen will transfer the hydrochloric acid will transfer that hydrogen to the water. So in this case, water is acting as a base. It is accepting the hydrogen. So our hydrochloric acid is a proton donor, and our water is a proton acceptor. Okay, so that is how we define those. If it's going to donate the hydrogen, it is an acid. If it's going to accept the hydrogen, then it's a base. And then you just write out what's left, right? So then we are left with our chloride and our H3O+. So this, fits that Bronsted-Lowry definition. Okay, so bases are hydrogen acceptors. So any material with lone pairs could potentially be a Bronsted-Lowry base. So really anything that contains like nitrogen or oxygen, right? That could be potentially a base. But again, because of the structure of the molecule, there's often one nitrogen or one oxygen that is more willing to accept those hydrogens than others. Spoiler alert, most times in this class, it's going to be the nitrogen that's going to be accepting the hydrogens. Okay. Sometimes it will be an oxygen, but a lot of times it will be a nitrogen and often from a weak base. More on that later. So let's take ammonia as an example. And again, ammonia was our weak base. When we put ammonia in water, what happens, right? Because this is a base, it is going to accept one of these hydrogens. So it's going to pull one of the hydrogens off of water. So in this case, and I guess my arrow would be better served going the other way. In this case, water is acting as an acid because it is going to donate a hydrogen to the ammonia. And so this makes ammonium and hydroxide. Okay, so water in the previous example acted as a base, and in this example, it acted as an acid, right? So that should strike you as a little bit odd. And water is what we call an amphoteric substance. And this is something that can act as either an acid or a base because they have a transferable hydrogen, right? An acidic hydrogen. And they also have a lone pair of electrons. So anything that meets both of those criteria can be amphoteric. It can sometimes act as an acid, it can sometimes act as a base. And it's just going to depend on what you pair it with. So like if you stick water with an acid, water's like, okay, cool, I will act as a base. If you put water with a base, it will act like an acid. Okay, so water will just kind of be whatever is the opposite of whatever you stuck in it. So we have our acid plus our base here, and then we have our base plus our acid down here. Okay, so again, it will act, the opposite of whatever you're adding to it. All right, let's go ahead and practice this. So here are some practice problems, and I want you to identify whether water is acting as an acid or a base in the following reactions. Okay, what I want you to think about, this Bronsted-Lowry definition, and I want you to consider whether water is accepting a proton or whether water is donating a proton. Okay, so go ahead, pause here, try and figure this out, come back when you're ready. Okay, let's go over this. So in the first one we just went over, right? Hydrochloric acid is an acid. Therefore, water should act like a base. And the way you would see that, so we look and see what happened over here. Okay, this is H3O+. So to get from water to H3O+, what happened is that it accepted a proton. Okay, and so if it accepted a proton, that means water was a base. Again, here we talked about this next one before where ammonia was a base and water was acting like an acid, but let's say we didn't know that. So water turned into hydroxide. Okay, so what happened? It donated a proton. So since it donated a proton, that means that water in that case was acting like an acid. All right, in this next one, water went from H2O to H3O+. That means that water accepted a proton, therefore water was a base. Okay, that means that this guy, ammonium, that was an acid. All right, in this last one, we'll look, water went from H2O to H3O+. That means, again, it accepted a proton, therefore it was acting like a base. So that means this was an acid, this was a base. Okay, so again, all you're trying to figure out is, did it accept a proton? Did it donate a proton? All right. Acid-base reactions in this Bronsted-Lowry definition is that we will write them as reversible reactions. I talked about a little bit with the strong acids and strong bases. Those we are going to write with one-way arrows because their equilibrium is essentially so complete, right? We've talked about that before. They actually don't even report K values for these strong acids and strong bases because essentially every single molecule will dissociate. Okay, but oftentimes when we have weak acids and weak bases, now we can write them as reversible reactions. And this is because when we have this hydrogen, right, and we donate it to our base. Okay, so here now we have our hydrogen is bonded to our base, and our, the rest of our acid, right, the part that's left is floating around by itself. Well, once that happens, now our acid has a lone pair, right? What's left over from our acid has a lone pair, and now our base has an acidic hydrogen. So we could totally flip it around, right? And they can re-react and form the original reactants. Okay, so this is a reversible reaction because we turn our acid essentially back into a base, and we turn our base into an acid. So they can go, undergo another acid-base reaction. Okay, so they are reversible. And so we have terms that we call these things, right? The leftover bits that I keep alluding to. In a Bronsted-Lowry acid-base reaction, our original base will become an acid in the reverse reaction, right? If they were to go back and reform the reactants. And the original acid will become a base in the reverse reaction. Okay, and so we call these conjugate acid-base pairs. All right, so let's say we started off with ammonia. And, ammonia reacted with water, right? And when it did that, it accepted one of those hydrogens and it made NH4 plus and OH minus. Okay, so here, ammonia acted like a base, water acted like an acid. Once ammonia gains a hydrogen, okay, now we call it the conjugate acid. So it started as a base. After it accepts a hydrogen, now it is the conjugate acid of ammonia. Okay, similar over here. If we have water acting like an acid and it got one of those hydrogens pulled off, now hydroxide is the conjugate base of our acid. Okay, the only way that these are different, guys, is that they have either gained or lost a hydrogen. Okay, if it's gaining a hydrogen, right, that means it's going from a base to an acid. If it's losing a hydrogen, it's going from an acid to a base. But either way, we call these conjugate acid-base pairs. So here it is again. So if we have ammonia acting like a base, again, so this would be our base. So therefore, this is our conjugate acid. This is our acid. This is our conjugate base. Okay, and oftentimes if we were writing these on our homework assignments, I'll write them like this to shorthand it. Okay, so base plus acid gives you conjugate acid and conjugate base. So a base will always accept that proton and become a conjugate acid. An acid will donate a proton and become a conjugate base. All right, let's practice this a little bit. So we have 3 acids and 3 bases. So for the acids, I want you to tell me the formula of the conjugate base. And for the bases, I want you to tell me the formula of the conjugate acid. Again, remember, these are just going to differ by 1 hydrogen. Okay, so go ahead, pause here, try this out. Okay, so acids, remember, all of our acids are going to be proton donors, which means that they will lose a hydrogen. So when HF loses a hydrogen, it becomes F minus. Okay, when this is sulfurous acid, when it loses a hydrogen, it becomes HSO3 minus. So again, it didn't lose both of those hydrogens, right? It just lost one, and then it gained a negative charge. Okay, and then we have carbonic acid. Again, it's going to lose a proton, and it just loses one of them, and then it gains a negative charge. So these would all be acids, and these are the conjugate bases. Okay, so now we'll do the same thing for the bases. The difference here is that bases will always gain a proton, right? Bases are proton acceptors. All right, so now we're going to add a hydrogen on. So when we add a hydrogen on, then we lose our negative charge, right? And so we get H2PO4, or sorry, H3PO4. We increase our number of hydrogens. The next one, people are really tempted to balance out both of that 2 minus, right, and write H2SO3. Again, remember, when we're acting as a base, we're just gaining 1 hydrogen. So we're going to get HSO3, 1 minus. And then for the last one, we have our nitric acid. We'll get that hydrogen. Let's do one more. So if we had this guy, this is methylamine. Okay, so again, that's going to be a base. And the way that we're going to recognize this as a base in this class is the fact that there is a nitrogen with some hydrogens on it. Okay, it's a terminal nitrogen. And that's going to have a free lone pair that it can use to gain a hydrogen. All right, so now that nitrogen can gain our hydrogen, and so we can write CH3, NH3, but when it gains it, remember, it's going to become a 1 plus. The reason these didn't is because they were all negatively charged, but if it was neutral, now it's going to have a positive charge. Okay, and that is the end of today's lecture. So today we did a little bit of introduction to acids and bases in general. We talked about Arrhenius definitions of acids and bases. We talked about Bronsted-Lowry acids and bases, and we also looked at acid-base reactions and conjugate acid-base pairs. Okay, so make sure you start, working on that lecture worksheet. You don't have a ton to do yet, but it's coming. So make sure you don't fall behind. This is a very, very, very long lecture worksheet. Okay, I think there are 28 pages or so. So make sure you start working on that. There are lots of practice problems for you in there. And as always, if you have any questions about any of this, please send me a message and I will be happy to answer you. Otherwise, I will see you guys next time.